for joining us today. Thank you, Jimmy, for the invitation. Today, we'll have a title of my talk is Fine-Tuning Stable Diffusion with Hugging Face and One API Optimizations on AWS. So my name is Eduardo Alvarez. I'm a Senior AI Solutions Engineer at Intel. And my day-to-day work involves leveraging Intel's technology stack to build interesting solutions that showcase all the great things that you can do with Intel software and hardware. And actually, the really cool thing about coming after Joy, I don't think this was planned, is that he did touch on one of the concepts that I'll be touching on as well, which is software hardware co-design and how we use that concept at Intel to deliver the optimized software for AI workloads. And at the end, I'll conclude with a nice little demo of this workload and a little bit of a walkthrough through the code. So hopefully, you software developers on the call will enjoy that as well, taking a look at some code and running something live. So first off, the workload that you'll see today is part of a project called Intel Cloud Optimization Modules. These are sets of open source reference architectures that my team owns the AI component of. And what we do is we develop open source code to ship into the community so you guys know how to leverage Intel's technology within the context of specific AI workloads in the cloud. So if you scan that QR code, that's going to take you to the Intel Cloud Optimization module page. And like Jimmy said, we'll be sharing these slides afterwards so you guys can end the recording. So you guys are welcome to scan it then. If you look on the right side, we do touch on, at the lowest level, the hardware, the different components like Intel's new GPUs, the Intel's Xeon processors, and soon to come into these workloads, some of the Gaudi 1 and Gaudi 2 accelerators that have been the talk of the town lately after we released our MLPerf results last week. So inside of each one of these, inside of the modules, you'll find things like tutorials, source code, white papers, office hours, and more. And for those office hours, you're welcome to come and engage with my team and learn more about these workloads, and we can help you troubleshoot them as you try to implement them on your end. So one of the major takeaways I'm excited about today is this idea of making sure that we're pairing the right software with the right hardware tools. And that's what I meant by it's really exciting to go after Joy, because he did touch on this very briefly. And the idea that we should ask ourselves all the time as AI engineers is, are we using the right software tools and are we running them on the right hardware? And this goes, I'm not trying to make this exclusively and say like, hey, come to Intel, ignore everybody else. I think this is a powerful concept that you should consider across the board, whether you're working with NVIDIA, AMD, or all the other processors. You should be thinking about the software you choose when you're running on that hardware, because you might be leaving quite a bit on the table. Because believe it or not, there is this concept of companies like Intel or NVIDIA or AMD. We design software tools or extensions or packages that are more apt at running optimally on our hardware than they are on other systems. And that's just because we have we own the IP, we know what's going on under the hood, and we can optimize as much as possible so you can get the most out of the hardware. So the best example that I typically use for this is like, you can think of it as like Tesla and superchargers, right? There are some electric cars that superchargers either don't work with, or they don't, charge those batteries as optimally for. But for Tesla, they know how their batteries work. They own the IP, they own the secret sauce, and they can make sure that their chargers, charge their cars as quickly as possible. Therefore, pairing those two together makes sense. And we call that software hardware co-design in this world, but you might just think of it colloquially as like being compute aware when you design AI solutions. So this is an example of that. Thinking about software hardware co-design. One of the examples here is, for example, within the 4th generation Intel Xeon processors, we have an instruction called Intel Advanced Matrix Extensions. And this extension allows for optimal memory management, being able to move larger chunks of data within each core, and also optimizing the size of matrices that we can compute in a single operation. And if this is a computer vision meetup, so everybody should be fairly up to date on neural networks. So we know that most of those operations taking place in neural networks are matrix operations. So just by looking at this, it should be very clear to you that management of data and improved matrix multiplication. This is an instruction that's designed to optimize deep learning workloads on a CPU. Where traditionally we would expect, these kind of optimizations, similar optimizations inside of like CUDA cores, for example, in NVIDIA processors. And that's an instruction that is, that's inside of the hardware. And then on the software side, we have things like Intel's extension for PyTorch, which allows us to leverage Intel AMX by just adding a couple lines of code. So we'll look at some of that today, but this concept of we have this software and we have this hardware that when paired together run best is something to consider, like I said, not just for Intel, but across the board. And the way we do that at Intel is we have from beginning to end, we start with optimizing different tools across the stack from engineering, from data engineering all the way through the deployment. We saw Joey mention OpenVINO, and then I just mentioned Intel's extension for PyTorch, but we do have extensions for things like scikit-learn. We have upstreamed optimizations for a ton of different frameworks all across the stack. And all of those, or most of those, are leveraging some aspect of our one API standard, and that is our it's essentially like our lower level optimization library. And if you would like to learn more about one API, I recommend checking it out. It's really cool. One of our biggest things with one API is trying to not only optimize for Intel hardware, but as an open standard and leveraging SYCL, we're able to create software that can be ported, across hardware. So you might write you might write a software program that can run with like basically no changes across, NVIDIA, AMD, the Apple processors, or whatever you'd like. So let's talk a little bit about today's workload. Now that we're done talking about that concept of software hardware co-design and why that's so important. And I try to preach this in almost every kind of talk I give because it's something that was very enlightening for me. So today's workload is based on actually some work we did with Julian Simon over in Hugging Face that was published about 1 or 2 months ago through Hugging Face. They did it on the Intel Developer Cloud, and I've replicated that work on AWS. And the idea is we're just doing distributed training on Intel 4th Generation Xeon processors and leveraging some of the techniques I just described by using the optimizations that are integrated into Hugging Face Accelerate, such as the Intel extension for PyTorch, and so on. We're going to be fine-tuning a stable diffusion model on the M7i instances, which are those 4th Gen Xeon instances. And that fine-tuning is going to happen on the Stable Diffusion 1.5, which is a text-to-image model, which is very popular, has about 8 million downloads in the past month. And like I mentioned, the key optimizations we'll look at are leveraging Intel's advanced matrix extensions and things like auto-mix precision training with BF16 and FP32. For those of you guys not familiar with what Stable Diffusion is, Stable Diffusion is essentially composed of 3 different models: a variational autoencoder, a text encoder with and clip, and a UNet. And the idea is during the fine-tuning or training, we're really only training that UNet model, and the other 2 are used to compute the latent encodings of the image and text inputs. So for example, what we're going to be doing today is taking that raw model from Hugging Face, downloading it using the transformers library. And we're going to be using the Deku data set in order to fine tune it on a couple of like these little Q images of little robots. And we're going to provide it a simple prompt afterwards, and then we'll hopefully get a relevant image after that. Okay. So before we move on to that, for those of you who are maybe not as familiar with distributed training and that process, this is something that I would say is rarely done in some companies over the past couple of years. I guess pre-2021, pre-2020, when we were dealing with much smaller neural networks, but with the use of with the proliferation of very large foundational models, distributed training, and particularly for fine tuning has become very popular. So I'll just talk about that concept very briefly. The idea of distributed training is that you're no longer working with like sequentially processing on a single node. So if you think about how that would work, you might move only one bit of data in a batch into your processor as you perform your training loop. Then the optimization, the forward backward pass, the optimization of the gradient, the calculation of the gradients, and the calculation of loss would all happen on the single processor, and you would just do that and then wait for the next batch. The idea with distributed training is that data can be passed to individual workers. So instead of passing one chunk of data at a time, we can pass 3 chunks of that data at a time in a single go. Then we perform the forward and backward pass on the worker nodes. We can then pass the gradients back to our master node. The master node can synchronize those gradients and calculate, we get an update on our loss. And then those synchronized gradients can be passed back to our workers. There's a lot of different ways that distributed training happens. There's like the algorithms that are used and the methodologies depend on a couple different things, like some of the collective operations, which are the different ways that we can consolidate the information across different nodes and optimize, and then go on to the next batch. And also, just like, for example, TensorFlow and PyTorch will have potentially different distributed training backends, and how they work will vary. But this is a very kind of vanilla way to understand it. And the theory, I guess, applies to, I guess, in general, to distributing training as a whole. But like I mentioned, so we'll update the workers' weights, and then we'll move on to the next batch of data. And like I mentioned something in that last slide, which is distributed training collective operations. So the idea is that for you to be able to manage all that entire workload across multiple nodes, you have to have something that is managing the consolidation of the weights, consolidation of the gradients, optimizing, communicating across those different nodes. And within the one API standard, we do have a package called, or a library called 1CCL, which is the collective communications library. And the collective communications library contains things called collective operations, which allow the workers and the master nodes to communicate and consolidate information. So there are 4 key collective operations that take place during distributed training. We have scatter, which essentially creates an array of scattered data to distribute out into our system or our cluster. Then we have the reduce, which is typically an operation that applies things like summation, maximization, calculates a maximum or a minimum. Then we have broadcast, which essentially allows a data to move from a single process, the process root, into the other processes in the communicator. And then we have all reduce, which is essentially bringing together the reduce and broadcast operations under one umbrella. And this is probably, if you have to remember one collective operation from today's talk, this is the one to remember. Essentially, if you think about all reduce, what it's doing, at least within the context of distributed training, is consolidating the different, gradients and calculating a let me just move back to the previous slide so I can show you. What it's doing is synchronizing those gradients, then moving them back and distributing them back to the worker nodes, so that in that next step, we all agree where we are in terms of the optimization process of this model. Okay. So that's a quick introduction to distributed training. I wanted to make sure that we were kind of baselined and understood what was going on in the back end as we run this workload. So for the stack for this particular workload in the demo I'll show today, we're running, like I mentioned, on the Intel Xeon Platinum processor, and we're running on the AWS infrastructure, particularly using EC2 instances. And like I said, we have a couple of Intel One API optimizations that are enabling all of this in this workload. Namely 1DNN, which is our deep neural network, like deep learning optimizations, and then 1CCL, which is the one we just discussed, the collective communications library. And then at the AI libraries level, we have more than just these. You know, we're using the typical ones, pandas, numpy, et cetera, for data processing. But specifically, we're using Hugging Face Accelerate, diffusers, and transformers, as well as PyTorch and components of the AI Analytics Toolkit, which is the Intel extension for PyTorch. Okay, and let's dig into some of these very briefly. So very quickly, just Intel 4th generation Xeon M75 instances on AWS. Like I mentioned earlier, this is the family of instances that are the 4th generation Xeon processors. So whenever you're running and you provision this instance, you can run a quick LSCPU to see what this looks like. The one that we're using in this demo is the M7i 4X large, which is a 16 vCPU and 32 gigabytes of RAM processor. So we're using 3 of those, 3 different nodes. And then we can also run LSCPU grep AMX in order to determine whether we do or don't have AMX enabled. This is important because until recently, some of these lower level optimizations were not enabled on the clouds. This is done for various reasons, such as trying to manage on their stacks. They're trying to manage the power consumption and things like that. So that's something to always check to make sure that AMX and whatever optimizations you're looking for are actually enabled on the machine. So you can run LSCPU pipe grep AMX, and then you'll see here, this is what you expect: AMX BF16, AMX tile, AMX int8, just to make sure that those optimizations are enabled. And like I mentioned earlier, this is a quick diagram of the particular optimizations that AMX enables, which is the improved memory management and the more efficient matrix multiplications. Now, again, tying back to that concept of software hardware co-design, just a quick touch on Intel's extension for PyTorch. You can install Intel's extension for PyTorch directly from PyPy, running pip install. Hold on. This is not correct. This is to install PyTorch. I'll get you guys the correct line. But if you scan this QR code right here, you'll see this will take you to the GitHub IO page, and then you'll have the correct command to run to install Intel's extension for PyTorch. Okay. But once you have it installed, there's only a couple lines that you need to add in order to optimize your workflow. So for example, obviously you have to import it, but then we use, right now it's imported as IPEX. So we'd run IPEX.optimize, pass it our model, pass it our optimizer, and then the D type that we want to use. So for example, by passing torch.bfloat16, and then also adding a line of code here, which wraps our training loop with the torch.cpu AMP autocast, we enable auto mix precision, which is essentially a model compression technique during training. So that will train models at mixed precision with BF16 and which is half precision, and FP32, which is full precision. And like I mentioned a second ago, the Intel extension for PyTorch optimizations come all the way up the stack through, but are mainly supported by our one API standard and one DNN. So now to understand the Hugging Face Accelerate, which is the key component of this demo and this workload, the cool thing is that Hugging Face Accelerate has essentially adopted and upstreamed a lot of the optimizations that Intel has. So for example, if you're running on Intel processors and you want to use Intel extension for PyTorch, and you also want to use, for example, half precision or mixed precision training with BF16 and FP32, you really just have to use the GUI that they provide, and you can select that. So for example, here, you'll see that there is literally a prompt that asks, do you want to use Intel PyTorch extension, IPEX, to speed up training on CPU? All you have to do is say yes, and that enables that training optimization. Okay, and then I don't have it pictured here, but I'll show it in the demo where we can select the BF16 optimization as well. A quick summary of the workflow. So the idea for what we're going to show in the demo in a couple of minutes is we have to add IPEX to the optimization in our training, IPEX optimizations to the training script. Then we'll set up a passwordless SSH in order to allow the different EC2 instances to communicate with each other. Like I said, we're using 3 M7i instances, EC2 instances in the AWS cloud. Then we'll copy the data set into all the nodes in the cluster. We'll build the accelerate configuration file, the Hugging Face accelerate configuration file with a little GUI that I showed. And then we'll submit the job using MPI run, and then that will start the mixed precision fine tuning with IPEX enabled using 1CCL and PyTorch. Okay. So I'll go ahead and switch screens and go to the demo. But Jimmy, just a quick check on time. How am I doing?
You're good to go.
Okay, awesome. Let me go ahead and switch screens here. All right, I'll stop sharing and switch to the other screen. Alrighty, so what you're seeing here is what I've done is I've SSH'd into the host machine, which is our master node, and I've done that through VS Code. So now we can go ahead and get started. So like I mentioned earlier, we can run lscpu to check out what processor we're running in. So you can see here that we're running on that Intel Platinum 4th generation Xeon. It has a total of 16 vCPUs. And then we also see here that we do have AMX enabled. And the key one, like I said, for training that you're looking for is AMX BF16 or BF16. Okay. So another way that you could just look for that real quick, like I said, is just grep running this right here, lscpu grep AMX, and you'll see that we have AMX enabled. Alrighty. So the first thing I want to show you guys is inside of this script right here, which, by the way, all of this will be available as an open source package and code base through our Intel Cloud Optimization modules. This one isn't published yet, but if you go to the Intel optimization module, cloud optimization module page, we'll have it updated there, I don't know, within a couple of weeks or so. So like I mentioned a second ago, really all you have to do to enable, as far as code is involved, to enable IPEX is you want to go ahead and import it. So we're going to go ahead and import Intel extension for PyTorch as IPEX. And then, like I mentioned earlier, we have three different models that are part of Stable Diffusion. So we have the UNet and the variational encoder. And what we do is we pass the model to this IPEX.optimize. We let accelerate determine the D type, which we provide in the GUI. And we do that for both of these models. And once we've done that for both of these models, we're good to go. The model's wrapped with IPEX and it can be optimized. The one thing I'll call out when you do this is, let me see if I can find it. Let me just do a quick search for accelerate. Okay, so what I'm trying to find is the actual where we pass the optimizer to accelerate. Let's see if I can find that real quick to show you guys. Okay, the idea, what I was trying to show you guys is that whenever you use Intel extension for PyTorch, you cannot pass your model to the accelerate preparation script. Right here. To accelerator.prepare. You don't want to pass your model to this when you're running Intel extension for PyTorch. That will be incompatible because it'll be kind of like duplicating the effort. And it'll think you're trying to do it during the inference step and it will fail. So just want to call that out to you folks in terms of making sure that when you're running accelerate with IPEX that you don't have that dependency conflict. Okay. All right, so now that we've looked in the code where we have Intel's extension for PyTorch enabled, I'll just call out very quickly inside whenever you guys, if you guys want to experiment with this cloud optimization module, we are going to include this a make file to allow you guys to set up your environment. So in order to set up your master node, all you need to do is run these different instructions to install Miniconda and install the various dependencies. And here, I didn't have it earlier in the slide, but for example, here, this is where we install Intel's extension for PyTorch. This is when we install the 1CCL PyTorch bindings, which are needed in order to coordinate between the collective communications library, and the PyTorch distributed training backend. And then here's where we install the transformers libraries and the PyTorch relevant libraries. Here we download, we can use this instruction to download the data set. And then lastly, we can use this instruction to essentially run a quick single node test, which we will do right now. So let's see, close this up. You just open up my terminal again. Okay, so we'll go ahead and, like I said, I'll open this up so you guys can see what I'm doing. We'll go ahead and run this this quick single node test. So we'll run make single node test, and this is just going to run the training, the fine tuning on a quick 5 steps, 5 training steps of this model, and it's going to run it just on the master node. So I'll go ahead and just run that real quick, and that will take a couple of moments. So see that going on there. So we started training, and then again, just very quick 5 steps, nothing really meaningful, nothing major happening there. And then when the model's trained, we have it saved as a safe tensor inside of this folder. So we have those learned embeddings. Okay. So that is just for a quick look at training that model on a single node, making sure that our individual nodes are properly configured. The next thing we want to do is we want to actually configure our accelerate, our accelerate configuration file. So I'll run accelerate.config, accelerate space config, and this is going to prompt me with the GUI to complete a couple of steps here. So the first one is it's asking me what environment I'm running on. So I'm not running on Amazon SageMaker. I'm actually running on this, on my individual EC2 machines. And then I can select what kind of training I'm doing. So I could be doing on tensor processing units from Google, NPUs, GPUs, XPUs. But in this case, we're running with our CPU. So hit that. And then I can say how many machines I'm using. So I'm using 3 individual nodes, including my masters. So 2 workers, 1 master. And then the current machine I'm on is actually the master node, which corresponds to the 0 rank. So I'll leave that at 0. To retrieve the IP address of my host machine, I already have that configured in my SSH folder. So this is my host machine IP. It's okay. You guys can't really do anything with that, so I'm not worried if you guys see it. And then what port I want to use to communicate throughout the process. Typically with Accelerate, people use port 29500, but really any available port will work. We are running on the cloud, so we'll go ahead and say no. And then our rendezvous backend is going to be static. And then this is where I can determine whether I want to use Intel's extension for PyTorch or not. In this case, we are, so we'll say yes. Do we want to optimize our script with Torch Dynamo? We won't do that for now. And then how many CPUs I want to use for training. This actually refers to the number of sockets in the machine. And on a VM, like an EC2 machine that we're running on right now, we're probably typically working with just 1 socket. You can run LSCPU to check how many sockets you have. But in this case, I already know that we have just a single socket machine where we're running. So I'll type in 1. And then here's where I can select whether I want to use FP16 or BF16 for training. So I'll go ahead and use BF16, which is going to allow that mixed precision training, which is that during training mixed precision model compression technique that I mentioned earlier. Okay. So now my file has been saved, and I'll show you guys where that gets saved. So we can go to, I think it's yes, to our cache, Hugging Face, Accelerate, and we can see the configuration script here. So basically all we did through that GUI is set this up, but GUIs are nice, right? And especially if it's just like something quick in the terminal, no big headaches there. And that honestly is pretty much it. The only thing I'm not going to show in this demo is the configuration of the passwordless SSH, because that's something that's very well documented online. But I will say that one thing you do need to do, and I like to do just for sanity, is I go ahead and run this a configuration in each one of my nodes by hand if I only have a few nodes. Because it just, for me, it just saves it saves a headache. I know that I'm doing it correctly. But if you want to just copy and paste this configuration into your other machines, you can do that as well. And you can just point to it using accelerate when you execute your training command. Okay, just a couple more steps here. I want to show you guys very quickly, after you have a passwordless SSH set up, you can actually SSH into the other machines in your cluster. So I'm going to do that right now. And we're going to just SSH into our node number 1. And I'm going to open another terminal, and we're going to SSH into our node number 2. Okay, good to go. So what I want to do in each one of these is I want to run htop just so we have an interactive view of the compute that's being used inside each one of these. So we'll do that, and then let's see what else. Oh yeah, and I can just run an htop as well inside of our master node. And then we have htop running in each one of these. So we can see the compute that's being utilized. You can see our 16 different threads. Fairly no usage. Memory, again, about 120 out of 61. We're golden. Nothing major happening. I already typed in this command earlier, so I wouldn't have to type it in by hand right now. But let me just pull this up. This is the command we'll use to execute the distributed training job. So we'll run npi run. We specify our host file. Our host file is a file that has the names of all of our hosts. I typically just put it in my root directory. And then we pass the number of nodes and the number of processes that we want to run per machine. We're just going to run one process per machine. Then we run accelerate past accelerate launch, and we'll pass our training script to accelerate launch. And then we'll pass the various parameters. So for example, here we're passing the location of our training data. We are passing the placeholder token. We're passing things like the grading accumulation steps, the random seed, batch sizes, maximum number of training steps, learning rate, and so on. And also passing here a command to let it know that we do want to execute mixed precision training with BF16. Okay, so I'll go ahead and run this, and we'll give it a second to get started. So this is going to go ahead and run a couple things here in order to kick off the process, and then there we go. So we started training. So there it is, training across all machines. So to show you that, here's node number 1. And as it starts, you probably won't see full core utilization. That will take a couple of seconds. And then here's core node number 2. And then here's the process running on our master node. So this will go ahead and train across I didn't give it many steps, around 50, just to not eat up all the time in the demo. But we can see as the training runs, we see our memory utilization going up, and obviously the utilization of our threads going up as well, and varying as the process as the fine tuning takes place in a distributed fashion across all of these nodes. Okay. And like I said, one of the nice things I mentioned earlier is Accelerate makes it easy for us to not have to potentially use things like Kubernetes to do distributed training. Kubernetes is great, particularly I found that it's phenomenal for distributed inference, where you really need to scale up or scale down your process. But when you compare things like Intel's optimizations directly into the Hugging Face Accelerate library, and just with a couple lines of code in your training script, plus a quick configuration file, launch a distributed training job. I mean, it doesn't really get much better than that. And I'm really not just saying that as a Intel employee. I've run these workloads before coming to Intel, and I mean, it can be quite a bit of a nightmare to manage this, even with a tool like Kubernetes. So we have, you see here, now our core utilization has gone basically down to 0 on all 3 nodes. And we look back and we see here that yes, in fact, we have completed our distributed training. And then if I go back here, we'll see that we do have our model saved here. And I can't open this up because obviously these are learned embeddings saved as a safe tensor, so it's not going to be interpretable by the machine. But essentially, that's pretty much it. The next steps would be, if you wanted to take this the rest of the way would be to use maybe a tool like OpenVINO to deploy this model, like Joy kind of called out earlier. And you can use it to perform inference on and generate some cool images. And that will be something that we include inside of the optimization module when we release it. But yeah, that's it for me today, Jimmy.